Greetings and welcome, friends. Welcome, welcome indeed. We're starting a brand new zone, chapter, section, whatever. We're talking about vectors and parametric equations. We'll wait a little while on those parametrics, but vectors we're going to start talking about today. So today's lesson is about geometric vectors, and we're going to start off with a little bit of a vocabulario. First thing, it says a vector is a quantity that has both magnitude and direction. All right, so magnitude and direction. All right, so it's just a sample of a vector. I might have something like, I could call this vector A, which, by the way, the symbol here is kind of like, it's called a harpoon, actually, if you want. If you've, I don't know if you've ever like looked at names of symbols on your computadora, but the name of that symbol is a harpoon. It's not a full arrow, okay, because that would be referring to a ray, R-A-Y. And vector A would be something like this, all right? So it's got an initial point, and it has a set distance that it goes out. That's the magnitude. And it has an angle that I would be referring to. All right, so angle and magnitude. So the angle, I suppose I could call theta, and the magnitude of vector A is denoted with kind of like an absolute value symbol, which makes sense because if you think about absolute value shows up in two-dimensional distance formulas and stuff like that. So absolute value being a type of distance, magnitude is kind of referring to that distance. And that's what it says here. Magnitude is the length of a line segment representing a vector. So here's a line segment. Don't be confused with the arrow. I realize that looks as though this might infinitely travel in that direction. It does not, because there's a fixed length for vectors. The arrow is there merely to explain what direction we're traveling in. Okay, so a vector like that versus a vector like this, even if the magnitude's the same, this would be opposite.
At this time, the Halifax students and the students taking them over are dismissed.
Opposite. All right, let's see, standard position, vector with its initial point at the origin. That makes sense because we had standard position back in the day for angles. Basically, the angle's always going to be measured from the kind of rightmost side between the positive x-axis and the edge or side of our vector. All right, so angle referring to the direction is going to be measured kind of in those capacities. So that's standard position. Direction is the directed angle between the positive x-axis and the vector, like I indicated here. So why is it valuable to have this unit or quantity? Well, oftentimes in real world things, it's not, you don't just want to know speed, for instance, but you'd want to know velocity, where you know what direction you're traveling at what rate, because the direction will matter. So the vectors can be used to model all sorts of different things like trajectories and speeds and multiple forces being acted upon an object, different things like that. So we'll be seeing that throughout this section. Let's talk about a couple more terms. Oh no, I see a typo. Let's see. Oop, I fixed it. I fixed it though. It still counts. Don't worry, I didn't copy and paste it until I fixed the typo. Here we go. So you don't have to write these down for my friends within the class. You can always show you later, or pause the video if you watch it later, because I'm sure you're going to go home and watch this and give it all the likes and subscribes. So it says a zero vector has a magnitude of 0. One thing I'll also point, it's denoted as 0 with the little harpoon on it. Harpoon, all right, is a zero vector. So essentially a zero vector would just be like a direction, right? That'd be like saying like face north and don't do anything, don't move. All right, so it's just a direction. It says two vectors are equal if and only if they have the same direction and magnitude. All right, so let's say I've got the following. So here's a bunch of vectors. Let's throw some names on these. Say this is vector A, vector B, vector C, vector D, and vector E. All right. So which of the following two vectors are equal? Well, all of these have the same magnitude, or I tried to draw them that way, but they don't all have the same direction. Okay. These vectors have the same magnitude, but they're traveling in opposite directions. These two vectors happen to have the same magnitude and direction. All right, this vector and this vector, B and E, have the same direction but different magnitudes. Okay, so in order for vectors to be equal, their magnitudes and directions must be the same. All right. So that would be the idea behind that concept. So what we have, now that we understand kind of some basic concepts about vectors, we can actually start working with them in terms of adding them together and doing all sorts of cool stuff. Let me show you some cool stuff here, a little bit more vocabulario. A resultant, all right, is the sum of two or more vectors. Okay, so we're going to eventually get into that. And opposites are vectors that have the same magnitude but opposite directions. So the angles are 180-degree difference from one another, which, by the way, you guys will probably appreciate this. I believe vectors typically always use angles. I don't think I've ever seen them use radians. Sometimes they could use, I might describe like north, northwest or something like that. But then you can kind of translate that back into an angle in degrees if you're interested in that. So let's do a little example here though first. Before I can talk about adding, I got to talk about measuring vectors and whatnot. Let's say I wanted to measure the following vector, and I'm actually going to, ready for this? Skip out to real life. Ooh, almost. There we go. Let's see, I've got my, oh boy, is this lagging. Let's see, there it is, 90, Okay, so I've got my protractor, and I've got a little piece of paper here. So let me draw a vector here. Let's say this is my vector, all right? And I'll draw my horizontal there. Okay, so you guys could draw whatever vector you want, somewhere around that scale and size perhaps. So if I want to describe the size and direction, the magnitude and direction of this vector, oh, it just got blurry on us, guys, why? I'm going to use a protractor, which I've kindly equipped you with. So to find the magnitude, that's easy. I'll use centimeters here. So I'd start from the initial point. It looks like this is, I'll call that 3-ish centimeters, how about, right? So 3 centimeters. Let's see if I can even take a snapshot of this. That'll be good. So, oh, I just changed the scale. Well, it doesn't matter. So we'll call this 3 centimeters. All right. I also could have measured using inches on our, or no, what are those? Oh yeah, the inch starts from over here, which actually, this is actually a really bad measuring tool. You see how it's got like this curved edge there? It doesn't give you a very good starting point. Sometimes you'll see a fixed line showing after the curved edge of the measurement tool, so you can get a better result. But 3 centimeters is the overall magnitude. So if this was vector A, I could say that the magnitude of vector A is 3 centimeters. Okay, so now if I want to measure the angle, what I would do is you line up in your little crosshairs. Notice I've got my little crosshairs like so. Like that. Let me grab a snapshot of this guy right here. And yours is obviously going to be different. because I assume you didn't come over here and draw to scale exactly what I had done. So if I'm talking about the angle, first thing you got to do is line up the crosshairs. And your like little red dot scope there. Yeah, bam. And now you might notice that, oh, this isn't actually pointing very good for us. Sometimes what you have to do is actually re-extend kind of our line here a little bit, which you could actually even use another piece of paper or a note card or something like that. But you'd want to extend your line out until it's readable by the arc that we have. And the arc that I'm going by, let's see, do I want a number that's around 120 or 60?
120.
Yeah, because the 60 is actually measuring from 0 degrees over here, is what that's measuring from. The 120 was measuring from 0 over here, which is what I want because my positive x-axis over here per se. Right, so I'm looking at an angle, here's 125, here's 120. I don't know, you want to call that 123 maybe, because if I didn't have my little wobble. So the angle, I'll call it theta in this case, is 123 degrees. All right, so not too shabby. What's up, question?
If you're looking for the reference angle, you would use a 60 though, right?
Yeah, that would be my reference angle, yeah, or 57 or whatever that would be, yeah. Which actually, a challenge might be if you end up with an angle that is over 180 degrees. Let me see if I can quickly demonstrate. So if, say, this was my angle, and I'm like, oh man, that's over 180 degrees, what do I do? What you can do is draw the horizontal. Oh man, look at my Band-Aid now, forever on the internet. I cut my finger slicing up naranjas last night. How embarrassing. So I know that this is 180, and then to find the actual measurement, I'd flip my protractor upside down, and notice I'm not only lining up the crosshairs, but also the horizontal over here, and then I could measure the angle from here, and I can say this is like 50, perhaps. So I would just add 50 to 180 and get the 230 there. Is how you would accomplish angles that are beyond 180 using a protractor. It requires a little bit of angle addition postulate, if you would. Yeah. So let's talk about adding vectors. And there's two techniques for adding vectors. And it's related to the fact that I said earlier a resultant is the sum of two or more vectors. Now when I add two vectors, what do I expect to get in return? Turns out we'll get another vector. Okay? So this first technique is called the parallelogram method. All right. And the parallelogram method is quite cool. Imagine I've got this vector here. We'll call this vector Q. And I want to add that to vector P, let's say. And let's say I've got vector P is this size in that direction. So this could be used to model, say, like two forces acting on an object at the same time. What's the result of their combined forces, or resultant? What's the resultant vector? What I would actually do is draw a parallelogram. So here's Q. I would extend that off of the end of P and draw that there. And then I'd also draw the other little p right here. So here's P and Q again. And the resultant of both forces, does anyone know, is going to be the diagonal. So that would be P plus Q. Vector P plus Q, technically, right? Or vector P plus vector Q, perhaps. Right, maybe is the better way to say it. So two vectors, when you add them, you can draw this little parallelogram, and that works out just great. Parallelogram method doesn't necessarily work very well if you have a zero vector involved, however, but it does work just all right. The other method is called the triangle method. All right, which is also sometimes referred to as tip to tail. Wow.
Rick Goodman, please dial 202, please. I have a message for you in the Student Support Services office.
So here's vector q, and I would take, and actually you could add in any order. Just vectors are, the addition of vectors is commutative, and I would just take vector p and put it tip to tail kind of to the other vector, and then once again the diagonal of this triangle would end up being vector p plus vector q. All right, so that's the tip to tail method. So if you were adding vectors visually like this, and you knew their initial measurements using a protractor, what I would do is draw q originally out at its proper magnitude and angle, and then draw a new angle here and measure p out at that angle and magnitude, and be able to draw it that way. And if I wanted to say find out what the magnitude of PQ was, I could just measure that, all right, once again, and also measure the overall angle of the result. All right, so that's called a resultant. It is the outcome of adding two vectors. All right. So, and that's the idea, to add two vectors. You just kind of end up doing it out like that. So, let's talk about scalars real quick. More vocab coming at you. Hang on, friends. What's up? What's up? Nothing. All right. So, oh, scalars. Yeah, I didn't. Quantity being multiplied by another. I'll just say a number. Yep. So a scalar. When did we see these before? We saw them back in Math 4 when we were dealing with matrices, right? And if you multiplied a matrix by a scalar, all right, so like 2 times matrix A, all I did was I multiplied every element within the matrix by 2. All right, so it's the same exact idea here. So for instance, if I have a little example here. Suppose I've got some vector. Say this is vector A. If I wanted to find, say, 3A, well, all I would do is, oh, that's not quite the same direction, is I would just measure it out 3 times the magnitude. All right, the direction would remain unchanged. And I guess technically you could also realize that 3A is equal to vector A plus vector A plus vector A, right? If I just think about tip to tail method, the resultant of that sum is the same as 3 times A. Right, so that's kind of how you can deal with that. So let's do a little example of the following. Cruising right along here. This might end up being my last example. We'll see. So let's say I want to find 2 times vector v plus -1/2 vector w. And let's say the following here. Let's say this is vector v. And we'll make up a vector w here, w. Yeah, that's fine. Dubs. There. So if I want to deal with that, I'm going to use the tip-to-tail method. So 2 times vector v. There's 1 vector v. There's another vector v. Let's see if I gave myself enough room. Half of vector w, all right, would be this distance, all right, half its overall length, but it's negative a half. What do you think is going to happen when it's negative?
Switches direction.
Yeah, it just simply changes direction. So here's what a full w would have been. A negative half w, all right, would have been just to this point, half the overall distance. Maybe I'll just draw it like that. So this is negative 1/2 w right there. And this was 2v. And so if I wanted to combine those, my actual answer, I just draw the overall diagonal here. And this is my answer of 2v plus negative 1/2 w.
So what is 1/2 w?
Half of w would have been this overall, this vector here, where it's just half the magnitude. And then an opposite vector just changes direction. So you could add 180 degrees to its angle, or subtract it dependingly, I guess, if you want to think about it that way. So yeah, let's see. I think I can give you the one last vocab term, because it does apply to this. We didn't get to all the examples, but that's fine. That's fine. We learned ourselves good today. Components. 2 or more vectors whose sum is a given vector are called components of the given vector. All right, so the resultant was the sum. Components would have been the little guys that were added together to make it. And oftentimes in the world of vectors, so say I had this vector, we often break up a vector into its horizontal and vertical components, where I might call this x and y. All right, and so horizontal and vertical components are often helpful for simplifying an overall problem, so that we don't get as confused by other stuff going on. And yeah, so that's the idea behind components. It's just write those there, or right, the 2v and the negative 1/2 w are technically also components. All right, well, thanks for watching, Internet friends. Have a great day. Bye-bye.